Alright, silly people, here's the situation. We have a Fourier series um, here, constants a(n) and bn on the sine and cosine functions. And first of all, we're going to prove that it can also be written like this, uh, but we'll have to make allusion to relationships between the constants given there, between cn and an and bn. So for the first thing I'm going to do is I'm actually going to explicitly write out the 0th term uh, of the Fourier series. So it's going to be a0 times the sine of 0 plus b0 cosine 0. And then everything else after 0 can be right in there. There's a sine and pi x over a and a cosine. Um, and cosine or sine of 0 is just 0, so that goes away, and cosine of 0 is just 1. And we can also expand the sine and cosine functions using the exponential definitions of those. We'll have an, and then this is going to be e to the in pi x over a minus e to the minus in pi x over a all over 2i. And the same thing for cosine, we'll expand it into the exponential form like this. And this is going to be over 2. So, okay, let's actually now regroup it into a couple of different sums, one of which I want to be from n equals 1 to infinity of e to the in pi x over a. And it's going to have the constants an over 2i plus bn over 2. And then you'll have another sum, also n equals 1 to infinity, just of e to the minus in pi x over a times, this is going to be minus an over 2i plus bn over 2. And I think that captures everything. And I think this is the weirdest part of the whole thing, is I'm going to take the second of those sums. The first sum is fine, but I'm going to take the second of those sums and switch the bounds. So now instead of going from 1 to infinity, we're going to go to minus infinity to 1, effectively switching the sign of n everywhere where it shows up in this sum. So we switch the sign of n here, so this is now a plus exponential. And then these constants are now not determined by n, but they're determined by minus n. So this is going to be b minus n over 2. Comparing with the other form of the Fourier series, I'm also going to explicitly write out the 0th term, so c0, and then e to the 0 is just 1, so it's just that. And then you get a couple of different sums, because 0 is in the middle of minus infinity to infinity. You'll have 1, where n is running from minus infinity to minus 1. I was definitely meant to change the sign here. That should be minus 1. But continuing with what I was doing, minus infinity to minus 1 of the stuff, so pi x over a, but then also a sum from 1 to infinity of the stuff. And now you see why I did this shit to the other form of the Fourier transform. Because now you can just make a direct comparison of all the constants, because these now all have the same powers of the exponential functions. So it looks like Cn has this relationship with An and Bn. And I'm going to make a big curly bracket. For n equals 0, C0 is just going to be equal to B0. So nothing crazy there. And then for n is greater than 0, we'll compare this constant with this constant, and we'll say that it's Cn equals An over 2i plus Bn over 2. And then for n less than 0, we'll compare this constant with this constant, and we see that it's Cn equals minus a minus n over 2i plus b to the minus n over 2. And then, yeah, you can just kind of leave it like that, and that's the relationship between the constants. And we get a form of the Fourier series, which is a lot nicer to work with because it only involves the calculation of one constant, which depends on n. And then this is n pi x over a. Okay. Then the problem asks, how do we actually calculate c sub n? And we can use Fourier's trick to figure this out. So what you do is you multiply both sides of the equation by e to the minus I n pi x over a. And this is fx on the left-hand side. It's not a sum anymore because now we have n on both sides, so this will just calculate a general property for a particular value then. So on the right-hand side we have a Cn, and then this minus this is 0, so any of the 0 is 1, so we'll just leave it like that. And then you integrate both sides. So left-hand side, you'll take the integral from negative a to a, and pi x over a, and then this is going to be fx dx, and then on the old right-hand side, we do the same integration bounds and the same integration. But on the right-hand side, that is a integral that has a closed solution. It's just 2a. So we can move that 2a to the other side, and we can say that 1 over 2a times the integral thing, fx dx is Cn. Ding, 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 ding. You got that form now. The next thing the problem asks you to do is to make some coordinate transformations. Particularly, you're changing n via this equation, defining k as n pi over a. And you're changing Cn using this equation, that capital F of k is equal to the square root of 2 over pi times a Cn, right? And what I'm going to do is I'm just going to solve for n and Cn and plug them in to this equation and this equation and just get new stuff. So I'm going to say n is going to be ak over pi, and Cn is going to be 1 over a root pi over 2 capital F of k. And I'm going to plug all that stuff into this equation up here, which is the Fourier series. So now we have that f of x will be given by the sum of k goes to minus infinity to infinity of 1 over a square root pi over 2 um, capital F of k, and then we have a e to the, or I'll just write it as a big exponent because it's going to be I pi x over a, and then plug in what we got for n, so it's ak over pi, and we'll get some cancellation in there. So moving the constants outside, you get something, or let me actually sum over all values of k, minus infinity to infinity, f k e to the I k x. My handwriting is terrible. I k x. That's one of the equations that we were meant to find, except there should be another additional constant on there, which Griffiths calls delta k, which is secretly dk dn, but don't worry about it. So we'll just take the derivative of this and call it just pi over a. So multiplying this equation by delta k inside of the sum and a over pi on the outside to make sure we're basically just multiplying by 1. So this is valid. And then the delta k will pull up in here. And then we get a nice bit of cancellation, and the radical of the pi just ends up being a radical on the bottom instead. And we have now the form that Griffiths wanted for this whole shebang. And then we also need to change this equation around to accommodate the coordinate transformation. So again, I'm just going to plug in C, N, and F wherever they pop up. So this will be the integral from minus a to a. We already saw that this just goes now to minus I k x. We have f of x, we got dx. On the right hand side we have square root of pi over 2 divided by a times f of k. And we'll just solve for f of k. So we'll get square root 1 over 2 pi. Yeah, times this stuff. That was me dropping my pen. Equals f of k. And yeah, that's another form of the equations that old Griffiths wanted. So we get to the last step where we take the limit of these equations as a goes to infinity. So this is the Fourier transform stuff. So in the limit where a goes to infinity of k, which will be the limit as a goes to infinity of a n over pi. No, it's pi n over a. This is funky because when a goes to infinity, this thing becomes infinitesimal, which is also interesting because now delta k since it's an infinitesimal quantity, we'll just go to dk. And now we can do an integral over all space rather than a sum over all values. So we'll have f of x just be 1 over root 2 pi, and it's at the integral now from minus infinity to infinity of the capital thing dk. And then, easily enough, we can apply the same limit here, but then just put infinities where we see a's. So this is going to be minus infinity to infinity e to the minus I k x, little f of x dx will be f of k. And now we have Fourier transforms. So that's pretty cool.